Hello everyone, I'm Kamil Bashkovich from DeltaRail, and over the next 15-20 minutes I will take you through our success story and tell you how we use Eclipse Paho and Eclipse Mosquitto to run quite significant chunks of the UK railway network. So first I'll give you a super quick introduction to signaling control and the key concepts involved. Then I'll give you an overview of IECC Scalable, our state-of-the-art signaling control and traffic management system, with a quick dive into the architecture and some of the reliability requirements that we have to meet. And then moving on to the Eclipse IoT components that we use in our system. And then finally some thoughts and best practices that we think might help you when working with those or similar technologies. So signaling. So first we've got tracks. So these are the railway tracks, big pieces of metal on which the trains actually move, plus some equipment alongside that can detect whether a train is in a given section of a track. So that's really important because from safety perspective, we need to know where the trains are and which sections of the railway are clear. The next bit are signals. So it's like traffic lights for trains, but there are some kind of subtle differences. So the main purpose of signals on the railway is to protect sections of track. So what you want to make sure is that there's only one train in a given section. So of course green means that the train can proceed, red means of course stop, and then there are some intermediate signals as well. The key difference with road traffic is that by default all signals are red, so trains have to stop, and only when the route has been enabled for a train to proceed, then the trains can go. And the third key element are pointer switches. So these effectively allow the trains to change direction of travel. So say you're traveling from Derby to Nottingham and London, at some point you'll be going through a number of those points, and then they will, depending on the position, they will make the train go to Nottingham or London or any other kind of route. Another point is routes, so that's more kind of a logical component which facilitates signaling control, and that really facilitates setting of points and signals to make sure that trains can run. But the most important bit is an interlocking. So that's a safety critical device that implements logic to make sure you haven't got conflicting routes being set. So effectively, what you want to avoid is two trains being in the same section of the track. And also they act as data aggregators. So they pull in all the signals, tracks and points and other information together. And it can be up to 50, maybe 100 signals, similar number of tracks and some points. And they aggregate the data and ensure this kind of safety critical function within that group of objects and also adjacent interlockings. So how those interlockings look like? So first, we've got mechanical interlockings. These are quite old, about 170, I think, years old. Still in use, I believe, in some of the parts or remote parts of UK rail network. And how we operate is you effectively move those metal levers to change signals or points. And the way that the safety is implemented is at the kind of mechanical level. So you can't move two levels with conflicting kind of actions together. Then we move on to the kind of electrical or relay interlockings, where you start having buttons to push and set routes and allow train movement, as opposed to that kind of mechanical action. And then you've got the computer-based interlockings, from about 1980s until kind of now, and these really allow for computer-based signaling control. And that's where our system comes in. So IECC Scalable, that's the latest version of our signaling control and traffic management system. And there are kind of two components to it. A number of workstations, typically about 8 screens and a mouse and keyboard. The top row gives signalers the overview of what's going on in the area they're responsible for, and the bottom row allows them to fully interact and manage the railway, decide where the trains are going, and so on. And then all the back-end services and components running in cabinets, in server rooms. So typically, when we deploy that system at a site, you would see about 1 to maybe 6 workstations, so those kind of desks for a given area. And those areas we control is that. So the grey bit is the older version of the system, which dates back pre-MQTT days. Everything purple and blue, that's the more recent stuff. With blue bits, that's the latest version running Eclipse IoT, both Paho and Mosquitto. So you can see we've got some presence in Scotland, Edinburgh, then Newcastle, Tyneside, York, and then quite a lot of around London, mainly the western route, so going from Paddington all the way through Reading, Swindon, down to Bristol, and then Marylebone, Liverpool Street, and hopefully some more sites coming in the near future. So then moving on to the architecture. So the way I would like to describe it to you is taking into account 2 modes of operation. So one thing is the manual signaling control. So you've got signalers sitting at the workstation, seeing the state of the railway and deciding where trains should go. And for that, we've got, of course, the workstations at the top. So that's the 8 monitors. Can be any number of those workstations. And then at the bottom, the remote interlocking interface. And you might remember that each of those interlockings is effectively a data aggregator for all the signals, tracks, points, and other equipment that's on the ground. So we interface with those interlockings, we aggregate that data, and make it available to the workstation, so the signaler can see what's going on. But because on most of the UK railway network, there is no communication with the train itself, we use something called a train describer, which, based on the state of the infrastructure, so signals and track occupation, it can determine which trains are where. So it can say, this train occupying that piece of track is actually the one from Derby to Nottingham, and that train over there is the one going towards London, say. And then that information is presented to the signalers, and then they can decide exactly which path the train should take to fulfill its service. So that's the manual control. And then the more interesting one, which happens most of the time in the background, is the automated route setting. So for that, we've got those 2 components on the right-hand side. Effectively, a timetable gets loaded automatically into the system, and the automated route setting automatically tells the infrastructure which trains are going where, and always ahead of the train sets the route so the train doesn't have to stop at the red signal. In case of most deployments, about 95% of the traffic, I believe, is handled automatically. So the routes are just being set. And then the manual control is really reacting to something that is not right, or there are some unplanned schedules or services running. And then the last bit, system monitoring. So we've got self-monitoring and to some extent self-recovery, which then leads into our high availability target. So we've got quite a tight target to achieve to make sure that everything runs as you would expect. So that's 99.9995, which is about up to 13 seconds per month downtime allowed, or 2.5 minutes per year. And we achieved that easily. So it's good to know that those things are working well. and there are no issues. And we achieved that partially with software, hardware redundancy, and all those things mean that the system is very low in maintenance. And what's really important is at the core of the system, we use the Eclipse IoT components, and that's Eclipse Mosquitto and Eclipse Paho. So Mosquitto is the server side of the MQTT layer, providing communication between all those components effectively, and then Paho sitting at each of those components doing the client side of MQTT. And both deliver really high throughput and low latency messaging, which is really important because when things change on the railway, you want to make sure that the signalers and the rest of the system knows about those things as quickly as possible. So you're talking about milliseconds here. Information entering the boundary of our system and then being available to the workstation to then be displayed to the user. And another key element there is that with the use of MQTT and Mosquitto and Paho and TCP/IP communication, we allow both the workstations and the remote interlocking interface to be completely remote. So we've got our customers having one part of the system being tens of miles away from the rest of the system, from the core components, and I believe later this year we'll be also deploying the workstations, again sitting miles away from the rest of the system, and all effectively being handled by an instance of Eclipse Mosquitto. So it really handles long distances very well and ensures that the messaging are really going through the system quickly. So now, taking a slightly closer look to the Eclipse IoT components. So first is the Java client. So of course the Paho family has libraries for many languages, C, C++, Python, JavaScript, Java, C#, Go, and many others I believe will be coming. We use the Java client. For those who want to use it, it's kind of both synchronous, asynchronous APIs, depending the way you want to use it. But for us, the most important bit, it's highly resilient. So if you have any networking problems, like network switch problems, cables being pulled out, and so on, you want to make sure that your messaging layer recovers within seconds, not minutes. And that's what the Java client can give us. So if there are any problems with the network, it can gracefully recover from any problems within seconds to continue the operation. And then a fairly recent addition to the Paho family, MQTT Spy. Actually, it's been created specifically for testing IECC Scalable, as there was no other kind of suitable tool at that point to do the testing. And comes with many kind of power user features like advanced filtering, scripting, decoding custom message formats, decryption, and so on, but also suitable for basic pop sub. And then the kind of headless version of it to do automated testing or continuous integration, which is really important. The next bit, Eclipse Mosquitto. So that's really at the heart of the system. So very lightweight, production-grade MQTT broker, which is the server-side implementation of the MQTT protocol. It's really good at high throughput messaging, low latency. As mentioned before, it really messages bouncing through Mosquitto and back 3 times. You don't get latencies more than tens of milliseconds, typically. So that's really delivering the expectations. And since the first deployment with the latest version of IECC Scalable and Mosquitto in it, we've had over 20,000 hours of service and not a single problem. So it really shows how good it is. And finally, I wanted to take you through some of the lessons learned and best practices. So when we were architecting the system in the first place, we're considering various messaging options. And one of the choices at the time was publish, subscribe versus point-to-point. And a key thing to take into consideration is that with pub-sub, so one-to-many communication as opposed to point-to-point, you allow for adding new consumers of the data that you already have. So adding a new service that consumes the data you already produced, or adding new producers for the data to produce new requests. And that really allows adding those components without making changes to architecture or even the software that you wrote in the first place. And it significantly improves testability of the solution. And then the second key thing is quality of service. So if you kind of dive into messaging a bit more, there are kind of two ways of doing it. One is something called fire forget or cause zero, and one kind of persistent messaging where you've got guaranteed delivery. And on one hand, you would think that, yes, you want guaranteed delivery provided by the messaging layer, but then if you start taking account things like performance, maintenance, potential data loss and retry in some rare cases, so say your messaging server, the hardware dies, the hard disk dies, what do you do then? And if you actually take all those things into account and need to achieve 5 nines availability, you realize that you still need to implement some mechanisms to cater for data loss and do some retries. So again, if you take all those bits into account, then you kind of arrive at a conclusion that cause zero, basic fire and forget, is probably the best choice, because it means there's no disk I/O, it's all in-memory processing, which means it's very quick. You've got nothing to worry in terms of hardware failures, you just restart the server and it works again. So you've catered for data loss, and your messaging is completely stateless. And the more stateless components you have, the better, because it's easier to scale, easier to maintain. But then something that quite often I think gets forgotten is we talk about those messaging protocols for constrained devices being really good, low bandwidth, but then we put some JSON or some XML documents in the payload, and then it just expands so much. So what we found out is actually doing the compression of the payload on XML and JSON can give you up to 10, 20-fold compression rate with very low CPU usage. So that's worth considering, and you just do it once in the messaging layer and you get significant benefits. And then testability and test automation. So as mentioned with pub/sub, you allow for kind of interception or intercepting and injecting messages. So if you want to test a function of the system, just listen to what it's doing, just subscribe to a topic, if you of course allowed to, and you can test the behavior, or you can start injecting messages to pretend you're one of the components. So it significantly increases testability and makes it easier. And then test automation. It then makes both the functional and kind of non-functional performance, functional and non-functional testing much easier. So typically we would have, say, 5 workstations or maybe 3 workstations for a given site, but we can easily test 400 workstations to make sure that the system still behaves under either heavy load or some avalanche conditions. So these are the kind of the things we've learned, and we recommend you consider for those kind of projects. Any questions? And by the way, that's from one of the control centers nearby. If you have questions, feel free to ask them now, or if we run out of time, then just grab me during one of the coffee breaks and I'll be happy to answer. It's really, I think, up to you or the requirements or the architecture you're implementing. So traditionally, handling XML would be easier. You get loads of libraries to support that, and it's very efficient. You get XML schema validation, so that kind of more strict checking of the structure of the message and the content. So that's why maybe you would consider XML. These days we seem to be moving towards JSON, which is kind of less verbose but still quite a bit. And we're getting more and more support for validation and so on. So again, depending on what kind of components you're dealing with, if you use JavaScript, it'll be easier to use JSON. If you use C or C++ or Java, probably XML, but with Java you get support for both. So it really depends on the kind of languages you use. Yes. So because it's a safety-related system, we have to go through a number of hoops to certify the use of all that software for that particular case. So yes, we had to do that for Java, for all the libraries you use, including Mosquitto and Paho. But what you need to remember is you do it for a specific use case as opposed to getting a general approval for use of that particular component. So we apply security in depth, so that's at effectively every single layer of the system, starting from physical access, hardware, networking, operating system, and the application layer. So we've got at each level we implement security to make sure that it works and you can't get into it. So we interact with the interlockings, so that's provided by third party, and then that's where our system boundary is. So we get the data from the interlockings, so that's all the stuff that's on the ground, all the signals, tracks and so on, and we get the data feed effectively into our system, and that's running on pretty much standard servers to, of course, certain grade, but it's pretty much standard hardware, commercially available. So there are of course, a few levels of testing. There is developer testing, then more formal functional testing, non-functional testing that our testing performs, and that goes through a number of stages. And then there is formal testing with the data for a given site. So that's again full factory testing with all the potential states and various behavior. So it's like a staged process that we go through, and each change has to go through that. Yes, so internally we've got simulators for those interlockings. So of course, when we do the development, we use the simulators, which are very like for like in terms of the software. So we can run hours of simulated train movement throughout the system and test it. And when it then gets deployed to a site, it's then connected to real interlockings, tested before it gets commissioned, and then when it gets commissioned, then it starts running the railway. We use all sorts of methods to test it. One would be just randomly firing some messages to try to break the system on purpose. So it's not just positive testing. There is a lot of, I would call it, negative testing. We're effectively trying to break it. So one example is handling avalanche conditions. So in typical deployment, 3 workstations, but with the environment we've got in place, we can simulate 50 workstations, 100 workstations to make sure that when the system starts up or there is a failure on the railway with the interlockings, the system recovers instantly.
Perfect. Thank you.
Thank you, Ron.
Thank you, Camille.